So it's until 4:30 roughly.
Hmm?
Until 4:30.
4:30. Okay.
4:31.
It's fine. Yeah.
Okay, sit down, please. So this time I need to look out the title and it modified a bit. Shift equations of equivariant volumes, I think.
It's exercise for you. You're a chairman. That's why I didn't write it there. Yeah.
It's a pleasure to have Maxim here, please.
Okay, thank you very much. So let me start by thanking the organizers. It's a pleasure to come after COVID madness, I mean, to North America. So I haven't been around for 2 years, and especially in Toronto. So it's evening, people stress, so I will talk about very simple things. And so actually I will talk about very simple problem, which I think mathematicians didn't look up, and we actually were trying to solve very complicated problem, and then we realized that we don't know how to solve very simple problems. So we actually were studying Donaldson Thomas invariants, and we need some properties. So we needed to understand how things work with localization for non-compact manifold, and then we understood that nobody understands. So we wrote a paper. So this is paper which put in November with Nikita Nekrasov, then Nicola Piazzalunga, and myself. Then Michelle Vernier looked at our paper. She wrote some notes, and then we decided to put those notes as, you know, understanding what we did, I mean, as appendix to our paper. Okay, so let me try to explain for you the problem. So we're interested in applying Disterman-Heckman formula, right? So imagine we have a manifold, symplectic manifold, so we have a symplectic form. And then we would have some torus section on the manifold. And of course, I'm interested that this torus section is actually Hamiltonian. So I would say that I would have a vector fields, right, with some parameters VA. And then I would say that, you know, my V's are, so it will be D plus epsilon A IVA. This would kill omega plus epsilon A HA, right? So basically, this is my moment maps for this section. So I will have this property that IVA omega plus DHA equal to 0. Okay. And then, of course, what I'm interested, so for the sake of simplicity, I will assume that all my fixed points are isolated, etc. And then we know that there is a way of calculating this thing. So if I write for you the integral of my manifold X, E omega plus M, okay. It's a problem with some co-authors I write M, and with some co-authors I write X, and they're very insistent about it. I don't know why. So that's right. So then typically what we do, and again, for those who are very picky, I'm writing stuff up to 2 pi's, etc. So I'm not writing any 2 pi's. So the formula is telling us that this would be given by sum over fixed points. And there are some powers of 2 pi's. And then basically I have to write here, it will be epsilon A HA at fixed point. And then here I have to evaluate the square root of my you know, derivatives. But basically, roughly speaking, this will be some I of let me write, I mean, I for the fixed point. So these guys are not actually these epsilons. I have to calculate them. They will be typically linear combinations depending on the fixed point, right? So what is important that this thing is some basically a homogeneous polynomial in epsilons depending on my dimensionality. That's how the formula look like, right? And then this is wonderful. Well, I mean, these guys, so this is actually, right, so this would be a determinant, so I have to take a square root of d mu of my v nu at a fixed point. I have to evaluate. That's exactly the thing. So of course, I'm choosing a particular basis, but then when I look at particular fixed points, sometimes it will be just basically this local epsilons. This will be some linear combination of those epsilons. Okay, so this is a formula, and of course, now the standard thing. This is what most of the people are doing. Then what's the meaning of this integral? Because if M is compact, so if M is compact, right? So for example, I can take this side and expand an epsilon. Then I would have my integral over M. Then I will have omega d. So let me say that my dimension of manifold is 2d. Okay. Then I would have here next order will be epsilon a h a omega d m plus etc. And then here, of course, I have to expand this as well. Then, roughly speaking, if I will write, so that I will have a sum over fixed points, 1 over this epsilon I. Then there will be next term, if I expand, it will be epsilon a against epsilon I plus etc. But what is important that if I'm on compact manifold, this guy is well defined, right? So this is well defined integral. It's a number. So it's a number. So basically what I have some number plus terms of order of epsilon plus terms of order of epsilon squared, etc. So it means that if I look at this formula on that side, on the right-hand side, right? I mean, this is a more singular term. So for the compact guy, this guy should be 0. Then these guys typically should be 0. And then starting from basically the term which would look like order of epsilon 0, then all epsilon should magically disappear, and then then you get terms of order of epsilon. Yes.
How is 1 over epsilon 0? How can be 1 over epsilon equal to 0?
I have to sum over fixed points, so this is a magic. So of course this is not 0, but if I sum over fixed point, this will be 0, because otherwise I'm inconsistent, right? So this is a more singular term, and this should be regular. So this is for the compact. So for the compact, if you take, for example, I don't know, compact toric Euler manifold, this is a very efficient way of calculating, for example, this quantity. You just apply this formula, and then you write the result of the formula, and then, for example, you evaluate for epsilon equals 0, etc. That's what you are doing. So let's be a bit more concrete, for example, and try to actually think what we are doing and what we want to calculate, and then I will come where the issue lies. So again, I'm interested most of the time in this type of examples when I have a Cn and I will quotient by some bunch of U1s. So I'm basically interested in this toric Euler manifolds. Okay, so then my manifold, so I will basically need to write subscript T, which I will skip most of the time, but the idea is the following, that I will introduce the moment map. So I will have A. So then I will have, so let me say that I have coordinates zeta, I, and then I will just sometimes introduce zeta I square. So then I here will have my momentum map, which I can encode in the following way. For example, it's better to write it. Right. So this is just the numbers. This is what in physics sometimes people call charge matrix. And then I just have to look at my manifold mu. Right. Which is in this particular case is just it's abelian. Okay. Sorry. You tell me you cannot read my mu. I couldn't read your slides. Okay, mu A is equal to QA IPI. Which here? So mu A just index. So A runs from 1 to R, right? Right. So it runs. And then what I need to do, I need to say that my mu A is equal to some TA. So this is the values of moment map. So I'm going to this space, and then I'm basically quotienting by remaining U1s. Okay, and this would be giving me the space xt, which depends on T. So what is important, I have to specify, I have to order these T's somehow, because depending if I have a very complicated examples, then I have to think about chamber structure. If I choose different T's, I may end up with different manifolds. But typically the idea that if my T is close enough and they don't cross the chamber, then they're basically symplectomorphic. That's why I quite often will skip this T. It's a singular, right? Sometimes you have to look up what you have. And of course, what is important that typically you have to put certain conditions on these charges, on this matrix. If you don't want to, for example, avoid orbifolds or other type of singularities, there is typically some coprime conditions, okay? So I will do for you a very simple example at the moment. And so basically what we're interested, there are very nice formulas. And I apologize again. So now let me write text. I think it's because of Nekrasov likes to write text and somebody else, like, I don't know. So then I would like to basically understand how this integral can be written in terms of this data. And there is this old idea which goes back to Wheaton, and then it has been formalized, is the following thing. So let me introduce for you this object, which I will call f of epsilon t, which will look the following. So I will have an integral over 2n of zeta over cn. And then I will write here minus epsilon I pi. And then I will write here plus, sorry, let me write another integral, a from 1 to r, d phi a 2 pi I. And then that is just 2 pi. And then what do I want to write? Epsilon I pi plus I phi a q a pi minus ta. So this is actually a very simple integral. The idea is the following. So if I integrate over phi's, what I get the following thing. So this integral by definition will be integral over Cn, right? And then this, if I integrate over phi, I will just get a delta functions saying that mu over t equal ta, collection of delta functions, right? At the same time, this integral is invariant, under all my u1s. So in principle, there is a theorem which claims that this integral is supposed to be the same as integral on x of e omega. Sorry, this is not the same epsilons. I mean, there are always linear definitions. I will tell you in a moment. Okay, so this is typically the idea how you want to calculate these integrals. And again, you write formula this integral, this phi just gives you delta function, and then a priori you have just to integrate u integral over Cn on this delta function, and because it's invariant under u1, it goes to the quotient, and up to 2 pi's you get a volume. Now, what people realized this in 90s that you can do other way around. So let me, instead of integrating over phi, I can integrate over p instead. So if I integrate over p instead, then my integral will look is the following. So my integral will be f of t. So they will be product over a from 1 to r, d phi a over 2 pi I. And then above there, I will get e phi a t a. And then here I will get I from 1 to n epsilon I plus q I a phi a. So, well, integrate, yes, right. So this is right. I mean, what I'm saying that this is you just write in polar coordinates, whatever dr are, d phi, right? And this is exactly integration over p. And because p, this is just a linear integral, so this is just gives me exactly denominator. That's it.
T is a square modulus or square?
Square, right. So the integral which I'm taking here is just this integral from 0 to infinity dp e minus alpha p, and this is equal to 1 over alpha, right? Right. Yeah. Okay. So, and then what people realize that you can do this integral, and this integral is equal to this if you choose appropriately the contour. So for simple cases, you actually can do this very properly and see, how to choose the contour. So you should not take all poles, but in principle, if you take correct poles, which is basically will depend very much where your T lies. So you have to choose your T's, you have to close the contour, you have to do all these standard things, which is very easy to do in simple examples by hand, but becomes very complicated. But eventually, for the complicated integral, there is what's called Jeffrey-Kirwan prescription. So basically, those guys explain which poles to take, how to do it. You can put in Mathematica, but the whole idea that you just get this integral. So let's do a very simple example. So
after the prescription, it's a theorem.
It's a theorem, right? So in whatever 95 or 96 by Jeffrey and Kirwan, it has been proven. So basically, if you do this integral is the same as applying this stuff. So let me just do for you example, because I'm a bit messy with notation. So let's do this in the most simple example, CP1. Okay, so CP1 is exactly when we just quotient C2 by U1. So in my notation, this Q will be 1, 1, right? So my mu would be P1 plus P2, right? And so then if I look at moment maps, then I would say that mu over T, and then I'm quotient by U1, and I get CP1. So now if I stare at this integral, just what do I get? So the claim is the following, then the volume over T will be equal to 1 over 2 pi I d phi, and then here we'll have E phi T, and then I will have correspondingly epsilon 1 plus phi, epsilon 2 plus phi. Well, that's integral. So in this particular case, Jeffrey-Kirwan tells me that I have to take two poles. So what I will get the following answer. I will get minus epsilon 1 T epsilon 2 minus epsilon 1 plus E minus epsilon 2 T epsilon 1 minus epsilon 2. Then you start to expand things, and you can see right away that the constant terms get canceled. So if it starts from 1, these two terms cancels, and the next term will be T plus guys of order of epsilon. And because the space is compact, it's exactly, I mean, this term does not vanish. Okay. No, sorry. This term vanished here, right? It is volume. The volume is T. It's value of moment map, right? Volume of P1. No, I mean, I said to the beginning, I don't talk about 2 pi's. I'm saying this, but if you take a value of moment map, right, which is in normal ways, it's what, radius or whatever of sphere, then you reduce down, etc. So it's proportional to this number. Up to 2 pi's, which I said from beginning, I don't care.
So as Gilfant used to say, all constants are 1 except for 0.
Right.
Except we also had 0.
Right. But what is important here for compact case, when I expand these guys, these sort of singular terms cancel out. And that's exactly what corresponds to this very obvious statement. When I expand this side, all terms which are singular, they cancel out. Okay. So in principle, if I start to look at more complicated cases, right? So if I start to look when I have many moment maps, etc., then this will be very complicated function. But important thing that this guy will basically start from some homogeneous polynomial of T plus terms of order of epsilon. And this is homogeneous polynomial will be of degree TD, which is just complex dimensionality of the manifold. And of course, in principle, because I'm looking at the toric example, this polynomial, if I expand, if I write this as a sum over CA1 AD, TA1 TAD, so these guys actually have a very clean interpretation in terms of intersection numbers, because here the whole cohomology of XT will be generated by H2. It's because it's toric. So if I choose appropriate basis there, then basically these guys encode to me these numbers, intersection numbers, okay? So this is what I'm saying is the following thing. So these guys, imagine I choose some appropriate basis here, omega A. And then what I'm telling you that these numbers is just omega A, which omega AD. So this would be this number, A1, CAD. It's intersection numbers in my cohomology. So for example, in context of Calabi-Yau, people call it whatever Yukawa coupling. And, I mean, but it's intersection numbers in cohomology. Okay. And for example, for these toric examples, you know, exercise for you who has nothing better to do tonight. I mean, do example of CP2 or CP3. So the example of CP2 is just would be this example. So this would be d phi, E of phi t. And then you would have epsilon 1 plus phi, epsilon 2 plus phi, epsilon 3 plus phi. So when you actually will take all poles, you can again see that everything will cancel. There will be 3 singular terms and they will cancel anyway. And so you can have fun, okay? So this is pretty standard. It goes back to 90s, all the story. Okay, good. So now what the problem we were facing when we studied these things, then we wanted to understand how this story actually works. And there were a lot of claims for non-compact manifolds, okay? So again, let me apologize. Of course, I'm not teaching undergraduate class. I'm very sloppy. So of course, there are different type of epsilons here. I mean, these epsilons, it's actually related to the action on Cn. And then out of those epsilons, I can always read my epsilons on the quotient, because as you can see here, there is not epsilons on the ambient space appear, but only they're different. So there is only actually one parameter which you would expect, because there is only U1. So there are all these tricks and there are different redefinitions. This is basically related to the choosing the basis, okay? So now let's go to when X is non-compact. Okay, so for X being non-compact, so first of all, this formula is still true. So this is formula is true. But of course, the problem is the following, that what I wrote, it's a pity that I erased, but so when I will write to you this formula, which I will get again now over X fixed points, you know, E epsilon H product of some epsilons, etc. So now I cannot claim, because you know, I cannot say that I expand from this integral omega d, because this integral does not exist actually. So I cannot claim that it's actually regular. So I would know that I will start from a very singular term plus correction. So this would be a singular term. And then you will have more terms, and you will get some terms of order of epsilon, etc. So the problem we actually were facing, so again, we were doing totally different project, and but in the Calabi-Yau literature, in string literature, there are a lot of claims what people call intersection numbers for non-compact Calabi-Yauss. So there are, you can write, for example, basically you can write this for Calabi-Yauss threefolds, you can write these cubic polynomials and there are these numbers, okay? And people just say, oh, you do Poincare, do this and that, etc. And I mean, and then you get some numbers, and some numbers are fixed, not fixed. And then also we realize that, of course, these people are very inconsistent because some people write one version of polynomial, then somebody writes other version of polynomial. And of course, as a good boys, we wanted to do it by localization, right? So we wanted basically to take this formula, to take this integral, calculate, and do this sort of properly. And the thing is, for example, people already did this in the past. And if you look, so there is, for example, this old paper by Nekrasov, Shatashvili, Moore, when they did for some examples, this equivariant volumes. So typically you will get very singular term, then there are no terms, and then there is something, some polynomial which looks nice, which you would try to interpret the same way. And then you start to do more and more examples, because actually what you realize that, so when you start to do examples, when you reach the order of epsilon of order this, so when here you have a term of order of d, and then here you have order of this, right? So you're not even guaranteed that epsilon cancel, that it's, for example, depends only on epsilon. So if you go to complicate enough examples, there is no way to argue that this is the case. So actually, if you start to look at more and more complicated examples, the formulas are very, very messy. And for example, our first thing is that we look at the literature, we find one answer, we find another answer. So, and then we try to do a localization. We don't know how to get either this answer or that answer. So that was our problem. So we basically wanted to understand a structure of this formula for non-compact manifolds, and would like to understand if there are any better things to do. So just one comment here. Of course, all this story has a quantum mechanical picture. So there are a lot of generalizations. So for quantum mechanics, actually, what you can do is instead of S known, that instead of considering xt, consider in slightly different way. You can consider this space as a HCN stable. So you have to remove some points there, and you have to look at stable thing. And then you can basically quotient by C star action in R.
Why is it quantum mechanics?
Hmm?
Why is it quantum mechanics? Or in what sense?
In what sense? So what I will do is the following thing. So if I take my value of my moment map to be integers, then my symplectic form on the quotient will be quantized. So I can do geometrical quantization. And then I can count the sections there, okay? Right. And then if I count the sections, I can count them equivariantly. So on the big space, what I will just write, so my functions will be this sort of function. So I look at all possible z's in power ni. And then I have to see which guys descend down. And only those guys will descend down, which will satisfy this equation. So TA will be QA, I, and I. Where TA, it's basically, so it's H bar of TA. So you can, I mean, I have to quantize my T, otherwise, but anyhow, you can look how many sections you have there, and then you can write this object. Hmm? No. So what I can do, oops. So what I can write for you, I can write zeta q of t. So I can write a sum over qn equal to t. And then I will have here product of I, qi, and I, where q will be minus h of epsilon I. So I basically, this is a counting of my states, but I keep in U1 weights together. So if you want, for this very simple example, I can write for you for P1. So for P1, what I'm doing here, so correspondingly, this object will be zeta q of t will be equal sum over n1 plus n2 equal to t q1 of n1 q2 of n2. Okay. So now you basically, if you put up h bar, etc., you can see that if you take appropriate limit, this expression actually will go to that expression above. But this is just counting of states. Whoever studied quantum mechanics on the sphere knows how to do it. What is important here, so in a compact case, this is a polynomial. So this is a polynomial in Q. So again, Q's I can keep, I need Q's just to keep U1 weights. If I put Q to 1, I just get the integer number. So this will be dimensionality of the space. So if I put Q all Q's to 1, I just get the dimensionality of my Hilbert space. The problem is that if you take, for example, this formula and your manifold is non-compact, then of course my space is infinite dimensional and I cannot put, I mean, there is no meaning of dimensionality of the space. And this is exactly related to the singular terms. Okay. So let me just give you one simple example. Are there any questions? Yeah.
So if you consider your integral in the left-hand side as a kind of formal integral, would it be possible to find a system of differential equations for it as functions in epsilon? If it is possible, then you can try to find
there are some equations. So what I'm going to tell you, there are some different equations in T and involving epsilons. Right. And that would be basically the moral of my talk. There are shift equations. Yeah, you're a smart person. Okay. So let me give you maybe one example that you understand. So, you know, here P1, everything works fine, etc. Let's do a next simple example. For example, O minus 2 over P1. So O minus 2 over P1, it's this moment map, P1 minus 2P. It means a line bundle, O minus 2, yeah. So it's a very famous guy. It's a resolution of A1 singularity. So if you take a C2 over zeta 2, then you resolve it. This is a space, okay, plus P3. Okay. So now if I'm just doing this guy, so I'm looking at the moment map equal to T. And for example, I'm writing to you this, again, expression. So now my f of epsilon will be T, which will be 1 over 2 pi I d phi e phi of t, and then I will have here epsilon 1 plus phi, epsilon 2 minus 2 phi, epsilon 3 plus phi. So I'm just applying this formula which I wrote to you. Then actually I have to take here the poles. So now by convergence, actually, because my poles will have different signs, I mean, I don't have to take all poles. So this is where Jeffrey Kirwan is telling me. So I have to take this pole and this pole. So if I will do it, what I will get the following. I will get E minus epsilon 1 T, and then I will get epsilon 2 plus 2 epsilon 1, epsilon 3 minus epsilon 1, plus E minus epsilon 3 T, and then I will get here epsilon 2 plus 2 epsilon 3 epsilon 1 minus epsilon 3. So now you can expand it. You can see that it has a singular terms. So I mean, they will be terms of order of 1 over epsilon square. So I mean, it will start basically from this term, etc. So this is basically indication that the space is non-compact. The same thing, you can write a partition function. So partition function will be, for you, this zeta q of t will be equal to n1 minus 2 n2 plus n3 equal to t q1 n1 q2 n2 Q3 and 3. So you see this 2 minus 2 sign is very, very drastic sign. Right. It's exactly what tells me that if this would be a positive number, this would be a polynomial. But because it's negative, it's not a polynomial. It's basically a meromorphic function. Okay. And this is exactly related to this thing. So the question is, what we wanted to ask is that what's the structure of the singular terms, how they're regulated, what we can say, and if there is any meaningful way to define this intersection numbers, etc. So as has been pointed out already, that we need some equations, we need to understand what's going on. And for non-compact space, actually, there are more cohomologies in game. So of course you have a de Rham cohomology, right? So which we know very well. So for the compact case, we have a de Rham cohomology. Then, you know, of course you can invent a lot of cohomologies. So for example, you can start to invent L2 cohomology, which is very, very painful because it depends heavily on the metric. There are a lot of theorems. If you choose this metric with this decay, etc., etc. The only cohomology which is sort of universal, it's actually compactly supported cohomology. So of course you have a compactly supported cohomology. Okay. So now, of course, there is no way to say that this guy is part of this. I mean, they're sort of two different cohomologies. Okay. But there are some actions. So actually there exists the following action. So you can take your K form in de Rham plus K form compact and send to de Rham. So basically you take omega, I don't know, omega compactly supported, and then you construct omega plus omega compact, and that would be element in de Rham. Okay. Then there is actually existent, it's written, I think, in this book by Bott and Tu. There exists another map, which is done through Pankrat duality, that you can take a compact cohomology and map to de Rham cohomology. Okay. So actually, the compactly supported cohomology through Pankrat duality is the same as kth homology of my X. Okay. So of course I will look at very particular examples. So I will look at H2 of M because, you know, sorry, I have a schizophrenia, yeah. Okay, so I have this de Rham, and basically, since I'm looking at toric examples, everything is generated by this H2, and then I may have H2 compact. Okay, and then, you know, depending, sorry, I think I did it, it's D minus K, sorry. Okay, otherwise it's nonsense. Okay, so then I'm interested in this. Of course, not all manifolds will have these guys. So for example, if you want to look at 6-dimensional Calabi-Yau manifold or whatever, then it means that H4 fourth homology should be non-trivial. If it's trivial, then there are no elements like this. So actually, there are also one-to-one correspondence with what's called compact divisors. Compact divisors. So the divisors, I can think of my DI. If I take my quotient map and I will just put one of momenta to 0, and it just goes down to the quotient. That's what I will call a toric divisor. Again, it's not a proper definition, but I'm not giving a lecture in toric geometry. So this is again very new things which appears for non-compact geometry, is that there are very particular class of things which is we would call compact divisors. Compact divisor. So Pi is this momentum. So what I can do is the following thing. So I have my quotient, right? So I'm having Cn and then going down. And then there I have sort of some what's called divisors, roughly speaking, submanifolds. I can take a particular P, put it to 0 and look what's going on down. So let's just look at this, for example, of which I just wrote for you. So this example of O minus 2 over P1. So I have my mu is equal to P1 minus 2P2 plus P3 equal to T. So actually the compact divisors here is the following. So just look at this equation. So there is something very special about this P2. If I put P2 to 0, this is compact. So this is exactly what I will call a compact divisor. It's basically when I will look at this P2 equal to 0, and then I just do quotient, okay? So then you basically can analyze, you can write how, so if you choose the basis, so let me skip it, you're basically using, so let me skip it, but if you do this Poincare duality and you work out on particular basis how compact homology acts on this, then you get the following formula. So let me write for your formula and then explain it. So basically the equations will satisfy the following things. So if you take f epsilon of t, and then you will get E minus mi epsilon I f of well, we call it m, I will just explain. Then this will become a regular thing in these guys plus order of epsilon. So this is actually, if you want, this is concretely TA plus QA IMI. So I runs only over compact divisors.
So what's this F epsilon of T?
That's what I'm doing now for 40 minutes. This one. So f of epsilon of t, it's basically current volume. It's what we want to calculate. So this is one of the expressions. So the claim, this is a shift equation, the simplest version of this shift equations is the following thing, that if I take my volume and then I shift t's along basically the action of compact homology, I get something regular plus terms of order of epsilon. Okay. So this formula is actually requires you to analyze certain poles, etc. Now, let me give you a very shitty, not mathematical way of understanding this formula, but it's sort of intuitively very correct. So what you are doing here, you would like basically, what's roughly meaning of this? So this is not proper. So this is not a proof, but I have this integral, right? Omega d, which is not defined. Then I would like to subtract something like omega plus omega compact and take in power d, right? So what I will get terms, if I look at these guys, I will get terms omega compact plus omega d minus 1 plus etc. Now compact support means compact support. It just will be integrated over compact space. So this is well-defined terms, well-defined. So what I can do with the volume, so this guy is not defined, but what is defined that if I take my omega and shift by something compactly supported, then I should know the things. Again, I cannot actually write these equations at the level of differential forms. I have to write in the proper equivariant volumes, okay? So I have to keep these epsilons. But this basically equations tells me a lot about structure of singular terms. So let me try to tell you this stuff a bit. Of course, for the manifolds, what is important for me that I have to know all compact divisors. So there are how many MIs I have, it depends very much on my geometry. So for example, in this particular case, I just have one compact divisor. So when I put P2, etc. But the story becomes very interesting because typically the dimensionality of H2 and H compact can be very, very different. So I mean, one is empty, some is not empty, etc., etc. P of t. Oh, this is just some polynomial. So you have to calculate it's concrete polynomial. What is important here is non-trivial statement that if I do this shift, it's regular. It's regular. So then I can basically look at the term of order 0. Okay. And of course, what is important that this is concrete statement. So I take t, I shift my t by these parameters where I know that these guys run over compact divisors. Then magically you have to argue that appropriate poles cancel out, and this is regular. So this is basically the statement. And what did I want to say?
But this epsilon t is well defined, just it's like a
Right. Right. But I don't know what's the geometrical meaning. So I get a lot of the stuff, and I don't know what's geometrical meaning. And the more complicated examples you calculate, the more it's messy becomes. So that's what we basically did, and this is what mathematicians don't like to do. I mean, they develop theory, then they take some trivial line bundle over something, and they think the theory exists, and this is very misleading. For example, this example is very simple, but this is actually a very stupid example, because it's exactly the case when here H2 is one-dimensional, and H2 compact is one-dimensional. So it's sort of, I mean, a very, very silly example. Of course, if you look at more complicated examples, then you realize what's going on there. And basically, these equations you can start to solve. But what is important here, how you solve this equation, is the following thing. What you can see that if you look at this thing, you can try to put some t's to 0 by choosing appropriate m's. But what you have to do is the following, that you have this map. So this map Q is basically sent H2 compact to H2. But now I have to basically parameterize these guys. So I have to take this map, and then I have to choose co-kernel. So I have to, on some subspace, it will be invertible, my map. And then along those directions, I can put this to 0. And along other directions, I just have to, I cannot put it to 0. So, but this cannot be done canonically. I have to make choices. So what's going on roughly when you solve these equations, what you will realize is the following thing, that you will have f of epsilon some t's. So let me just look at the notations I want to use. So I will have some t, and I will have f of epsilon of t alpha 0. Okay. So T alpha, it's a basis. So this is a basis in co-kernel of my map Q. And then plus I will have some polynomial when I will evaluate T alpha. Then I will have some Q inverse on this Tij plus terms of order of epsilon. So intuitively, what's going on is the following, that if I'm, again, the whole thing is, this is why people got in the literature different definitions. So you can actually, there is no unique way to define intersection numbers unless you decide how you can sort of embed in certain basis of compact homology, inside of cohomology. You can do it, but you have to do it non-canonically. And once you do it, you will get these polynomials. And of course, depending how you choose your co-kernel, I mean, how you choose these coordinates, then you will get different things. Of course, this guys contains a lot of universal information. So certain things are fixed uniquely, certain numbers, but certain numbers are not fixed uniquely. So it's basically related, you know, which intersection numbers you calculate. So for example, I think I have to finish soon. So let me just talk about this intersection numbers. So in a way, what you are trying to do when you define the things, right? So I have to choose my basis omega A, omega B, omega C, right? Again, what I'm telling you, it's not very rigorous because you have to introduce epsilons, but roughly this is idea. So this is a basis in H2. So if I'm able to understand that some of the guys are compact, so for example, if this would be a compact guy, this is well defined. So whenever I have compact divisors, at least one compact divisor, then intersection numbers will be defined. And that's what people in the literature using algebraic geometry actually figure out. But there will be also intersection numbers of non-compact divisors, and they're not defined at all. You actually need to introduce epsilons to define them. And this is very non-canonical data. And then depending how you do the things in localization, this formula, you can do different choices and actually make different choices. So these guys contains very universal numbers, but not all numbers are fixed, because if you want to actually, this is example for 6-dimensional manifold. Okay, so let me just make a few statements. For quantum mechanics, you can actually write exactly the same story. So for quantum mechanics, you also can shift things along compact divisor, subtract between two partition functions, and basically you will get a polynomial. So I can structurally try to tell you how it looks like. So this analog shift equations for these guys will look like, so you have zeta q of t minus zeta q of t plus qm. So now this is integers, and this would be equal to a polynomial which depends on tm and q. So it's a polynomial in q. So again, idea that basically in these spaces you can look them as spaces which is foliated by compact divisor. Of course, again, this is a bit naive picture, because as you foliate your compact divisor, its topology may change, its partition, its partition function, its volumes can change. So you have to write it very carefully. So in principle, this story gets persistent. In the formula which I wrote for you, like basically when I write for you as a contour integral, so I write as a rational function, or I write some trigonometric functions. You can have write also some gamma functions, etc., etc. So this story is actually persistent, and you can even, so now with postdocs we are writing paper which is will describe also a Gromov-Witten invariance, at least at genus 0, etc. So the story is very, very persistent. And again, the main observation is that when you do this elementary calculations, people calculated everything, etc. But the structure actually, you have to, there is a lot of non-canonical structures, but it actually satisfies some very unique equations. And then depending how you solve these equations, you can deduce some information. Some information is unique, some it's not unique. But that's a way how you can define intersection numbers, because this guy you will call intersection polynomial for non-compact guy. But again, it's done non-canonically. You cannot do it canonically. Yeah, I think I don't know what to, I can tell you a lot of other examples, etc. But I think I would rather stop here. Of course, I can tell you a lot of examples. This is what we basically did in our paper. So we did some complicated examples. I don't know, Calabi-Yau 3-fold, 4-fold, 5-fold, and numbers, combinatorics, etc. And we thought that Michelle will try to also look at complicated examples, but she took a most simple example and explained properly for mathematicians what we did for the most simple example. But actually for us as a physicist, looking at very complicated examples was very important, because you start to understand the structures much better. And that was basically misconception in the literature. And even one of our co-authors, Nekrasov, we had to convince, because he told us he did everything in 90s. And I said, no, you just did the wrong case. So, there are some cases which is canonical, because when this map is invertible on the whole space, when these two spaces coincide in this, the solution is very simple. But when these spaces have a very different dimensionality, when you start to look at more examples, and especially also mathematicians and physicists like to look at the examples which is basically spaces which is some line bundles over some base, but actually they're very sort of special. There are other toric examples which is not line bundles. And again, there are a lot of numerology. So you can look up in our paper, you know, this is something we did Mathematica, Jeffrey Kirwan, residual Mathematica. I mean, so I think experimental Mathematica is good. That's my message. And then you can prove theorems. Okay, I will stop. Thank you.
The situation reminds me of renormalization a bit. And there's one procedure of making something regularized first. And one idea could be to go to a final volume and then put the volume to infinity, but there are also other regularization schemes.